SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied. Today we shall discuss about the reaction turbine. If we recall, in our last a few classes we have discussed about the impulse turbines, then we have also discussed about the need of compounding steam turbines, that is nothing but staging of steam turbines. So, today we shall discuss about the reaction turbine. We all know that these turbines are mechanical devices which are used to produce, they are an important part of the steam power plant, and when steam is allowed to flow through the turbines, we obtain work. So, turbines are basically work producing device. So, in turbine, steam which is produced from the boiler is allowed to flow through the flow nozzles, and then the steam jet which is coming out from the flow nozzle with high velocity, that steam jets impinge upon the blades of the turbine, and because of the impulsive effects, because of the both impulsive and reaction effects, turbine wheel rotates and we are getting work output. Now, the question is, so at the cost of some energy, of course, input energy, we are trying to obtain some work output, and that is how why these equipments, these turbines are very much essential for steam power plants. Now, if we try to recall, in the context of impulse turbine, we have discussed about the blading or diagram efficiency. The sole purpose was to figure out, to establish the efficiency, that means the fraction of input energy is getting converted into work output. So, to know that, even in the context of reaction turbine, we need to analyze the velocity triangles, we need to draw the velocity triangles, we need to analyze velocity components, and from there we shall try to quantify the efficiency which will give us an estimate about the work output from the input energy. We all know that the input energy is basically the kinetic energy of steam jets. So, the steam which is having high enthalpy, at the cost of that enthalpy drop would be getting some work output. So, the enthalpy of steam at the inlet to the turbine and enthalpy of steam at the exit of the turbine, if we can calculate. So, we can from there we can calculate the enthalpy drop, and from rather at the cost of that enthalpy drop, what would be the work output if we can somehow predict, and that will give us an estimation about or an estimate about the turbine efficiency. So, now before going to discuss about this, that is the blading efficiency or diagram efficiency of reaction turbine, let us briefly recall the basic difference that we also had discussed in one of the previous classes. An aspect for which reaction turbines are different from impulse turbines is the variation of pressure that we know. We had seen that while steam is passing through the turbines, of course impulse turbines, there is no pressure drop theoretically while steam is passing through the passage or blade passage. Now, again I am telling this is theoretical. In actual scenario there will be a drop in pressure, but you know theoretically there is no pressure drop when steam is passing through the blade passage. And we have also mentioned that we have also discussed that flow nozzles together with the blades, these two parts are the these two parts constitute the total steam turbine unit. So, basically for the impulse turbine, when steam is passing through the flow nozzle, that we have discussed, flow nozzles are also called as fixed blades. There is a pressure drop, and at the cost of that pressure drop there will be an increase in velocity of steam at the exit of the nozzle. So, the steam jet which is coming out from the flow nozzle will be having high kinetic energy, and that kinetic energy would be utilized to get the torque or work output. So, now that kinetic energy would be absorbed by the wheel of the turbine for the impulse turbine, but for the reaction turbine we have discussed pressure drop occurs when steam flows through the fixed blades or nozzles as well as through the moving blades or blades. So, this is an important difference between impulse and reaction turbines. So, basically in reaction turbines, in a reaction turbine when steam is passing through the blade passes, pressure drop occurs. Now, so basically we had seen that for the impulse turbine it is due to the impulsive effect, that is due to change in momentum difference that we have discussed, that steam jets will be deflected by the blade and that steam jet will suffer a loss of momentum and that momentum will be absorbed by the wheel. So, this is the impulsive effect, that is difference in momentum. In a reaction turbine that effect will be there over and above, since there will be a pressure drop when steam is passing through the blade passage, that is moving blades, steam will expand and there will be an increase in kinetic energy of steam jet, and it is because of this increase in kinetic energy of the exiting jet, a reaction force would be there in the opposite direction according to Newton's third law of motion. So, that means the turbine wheel will rotate due to both impulsive effect as well as the reaction of the exiting jet which is impressed on the blades in the opposite direction. So, it is basically an impulsive reaction turbine, but only to make it, to distinguish it from the impulse type turbine, we call it reaction turbine. So, let us now briefly draw the, so this is the nozzle or fixed blade. So, this is the first row of nozzles or fixed blades. and so these are blades or moving blades. So, these are this is the first row of blades or moving blades. Now, so basically blades, the passage between two consecutive blades forms a nozzle shape. So, when these two rows form a stage. So, these two rows, first row of nozzles or fixed blades and first row of blades or moving blades, these two rows together form a stage which is first stage. Now, this is the steam which is entering into the first row of nozzles or fixed blades, and that steam is coming out from the boiler, and that steam which will come out from the first row of nozzles will strike the first row of blades or moving blades, and again it will come out from the first row of blades or moving blades, it will enter into the second row of nozzles or fixed blades, and again second row of blades and moving blades like this. We have discussed about this particular aspect, that how many stages are required for the efficient operation of a turbine unit is is totally dependent on the total enthalpy drop. So, if we try to draw the pressure and velocity variation. So, now if we try to draw the velocity, so the velocity of steam which is, so this is V1, the velocity of steam that is coming out from the boiler and entering into the nozzle, and it is because of the pressure drop of steam inside the nozzle, there will be an increase in velocity of steam. So, this is V2, and see basically this is the first row of blades or moving blades. So, while steam is passing through the blade passage, the kinetic energy would be absorbed by the moving blades rows. Now, so basically that kinetic energy would be utilized to produce torque. So, what we can understand is that the velocity will drop. So, while steam is passing through the first row of moving blades or even second row of blades or moving blades, steam velocity will drop. Now, so this is the steam velocity. So, this is say V3. If we consider this is the if we consider only one stage, then this will be the velocity variation. Now, what about pressure? So, we all know that the pressure so if we try to draw the pressure variation here. So, this is the pressure, this is P1. We know that at the expense of pressure drop, steam velocity increases in the first row of moving blades or a first row of fixed blades or nozzle. So, pressure will fall. So, this is P2. Now, what we had seen for the impulse turbines, that pressure is remaining constant when steam is passing through the blade passage or moving blade passage. But in case of this type of turbine, that is reaction turbine, there will be a pressure drop when that steam is passing through the passage of the blades or moving blades. So, this is P3. Now, question is, as I said that while steam is passing through the blades passage or first row of blades or moving blades, second row of blades, third row of blades, pressure will drop. It is because of this pressure drop, kinetic energy of steam will increase. Now, from this variation we can understand that the velocity decreases, so kinetic energy would be kinetic energy will decrease. That is obvious because that energy would be absorbed by the wheel and that will produce torque. Question is, had we not allowed steam pressure to fall inside the moving blades or blades, velocity of steam inside the moving blade or at the exit of the moving blade, first row moving blade would have been even more. So, now velocity is what we can see from this diagram is V3, but it is because of this pressure drop velocity is V3. Now, let us consider a case when there is no pressure drop inside the first row of blades or moving blades. In such a case, the steam velocity would have been like this. So, that means it is because of this increase in velocity of steam, because of this drop in pressure, that kinetic energy increase will give rise to reaction in the opposite direction, and that reaction of the exiting jet impressed on the blades in the opposite direction, and that is why the wheel rotates because of both impulsive effect as well as this reaction effect, and hence it is called impulse reaction turbine or simply reaction turbine, only to distinguish this special type of turbine from the impulse turbine. So, now we had also defined one term that is called degree of reaction. That is defined as the ratio of enthalpy drop of steam in the moving blade to the total enthalpy drop, that is fixed blade plus enthalpy drop of steam in the moving blade. So, that is the degree of reaction. Now, so today we shall discuss about or we shall analyze the reaction turbine, of course, by drawing the velocity triangles only to establish the mathematical form of the blading work or diagram work or the diagram efficiency or blading efficiency. So, we will consider a particular case when R equal to half, that is 50% reaction turbine. It is obvious that when R equal to 0, then it is purely impulsive turbine. So, enthalpy drop of steam inside the moving blade is 0, and when R equal to 1, then you can understand that it is basically so when R equal to 0, then it is purely impulsive turbine, and when R equal to half, this is 50% reaction turbine that we are discussing, and when R equal to 1. So, basically we can understand when R equal to 1, then this is equal to 0, that means this is a purely reaction turbine. So, for R equal to half, that is 50% reaction turbine, this is the only one stage that we had drawn today to see the variation of pressure and velocity when stream is passing through the first row of blades or fixed blades, nozzles or fixed blades, and first row of blades or moving blades. So, if we try to draw the velocity triangle for this particular case, say r equal to half, then what we can understand for this particular case is delta H moving blade is equal to delta H fixed blade. So, that is enthalpy drop across the moving blade, enthalpy drop of steam while passing through the moving blades is equal to enthalpy drop of steam when passing through the nozzles or fixed blades. Now, for this case, if we go back to the this particular stage, then we can write, of course, this isentropic enthalpy drop. So, we can write this is equal to V2 square minus V1 square by 2, and this is equal to, so this is equal to V2 square minus V1 square by 2, that is in the fixed plates, and this is equal to, because this is moving blades. So, this is equal to VR3 square minus VR2 square divided by 2. So, basically what we can write is that for this particular case, if we try to draw the velocity triangles now, and here you know that V2, V1 are the absolute velocity of steam, V2 is absolute velocity of steam leaving the first row of nozzle or nozzles, and V1 is the absolute velocity of steam leaving the first row of nozzles, and VR3 and VR2, these are the relative velocity of steam. VR3 is relative velocity of steam leaving the first row of moving blades, VR2 is the relative velocity of steam entering into the first row of moving blades. But for the present analysis, we will be using the terminology C1 and C2 as the absolute velocity of steam, and W1 and W2 are the relative velocity of steam. Relative velocity of steam. So, if we draw the velocity triangle for this particular case, so this is the inlet velocity triangle. So, say this is the nozzle, stream is coming out, and this is the flow angle alpha. This is the blade angle beta 1, and the exit velocity triangle, if we try to superimpose on this plane, then so this is, so let me again identify the velocity components. So, this is basically C1, this is W1, that is the absolute velocity of steam leaving the coming out from the, say we are going to discuss in the so that say this is C1, So, this is instead of V1 we are assuming this is C1. As I said that we are going to consider C1 and C2 as the absolute velocity of steam, it is not V2 and V1. So, this is up to you, you also can use V2 and V1. So, now this is C1 and this is the flow angle alpha. So, I am writing alpha is the inlet flow angle, beta 1 is the blade angle at the inlet, and this is C2 and this is W2. So, C2 and W2 are the absolute velocity of steam leaving the nozzle and relative velocity of steam leaving the nozzle and entering into the first row of moving blades, and this is Vb, that is blade velocity. So, let me write here again. So, Vb is the blade velocity. Or blade velocity. So, this is basically we write pi dm n by 60. So, this is calculated based on the mean diameter. Now, this angle is the exit blade angle beta 2. So, this is beta 2. So, beta 2 is the exit blade angle, and so this is, if we try to now draw the so this is basically delta, this is basically delta c theta. So, now we will write it because we have also done similar type of analysis for the impulse type of turbine. So, what we can write that since we are going to consider a special case for which degree of reaction is half, for such a case we can write that C1 equal to W2. So, C1 equal to W2. So, for R equal to half, C1 equal to W2, that we will be getting from the expression of enthalpy drop across the moving blade and enthalpy drop across the nozzles or fixed blades. And for geometric similarity, for similar in geometry, because essentially blades are manufactured from the basically these are extruded from the same dies. So, they are geometrically similar, and for geometrical similarity we can write this alpha equal to beta 1, alpha equal to beta 1. In fact, this is a true case because blades of a turbine or blades of the turbine are manufactured from a extrusion process, and those are extruded from a same dies, and geometrical similarity is maintained. So, alpha equal to beta 1. So, this is the case. So, now if we try to give name of these two triangles that we have drawn here, say this is A, this is B, this is C, and this is D. So, what we had seen that C1 equal to W2, that means AC equal to BD, alpha equal to beta 1, that means angle DBC equal to angle BCA or ACB, and also VB is common because you can see that VB is same. So, blade velocity that is pi dm n by 60. So, VB is same. So, what we have studied in our class 10, we can see side angle side. So, we can compare these two triangles because these two triangles we can see from this diagram. Now, we can see that there is a common side, that is BC, other two sides are equal, that is AC and BD, two angles are same, that is angle DBC and angle ACB. So, from the understanding of side angle side similarity of two triangles, we can now compare. So, basically we can write angle triangle ABC and triangle BCD are similar. So, triangle ABC and triangle BDC are similar. And this is basically what I said, that from the concept of side angle side similarity of two triangles. So, basically we can say these two triangles are similar. If these two triangles are similar, then we can write that C2 would be equal to W1, right. So, then we can write C2 equal to W1, right, that we can write, and we say that all angles are measured in the clockwise direction, and say this is the angle gamma and this is the angle delta. So, we can see that beta 1 equal to, if these two triangles are similar, then this beta 1 would be equal to this angle and this beta 1 equal to 180 minus delta. So, try to understand, if these two triangles are similar, then this angle beta 1 would be equal to this angle, and so beta 1 equal to 180 minus delta, because this is the delta. So, from here we can write, and beta 1 equal to, let us give one name here, say this is E. So, this is E. So, this beta 1 equal to angle ACE, equal to 180 minus delta, that we can write easily, right, because these two triangles are similar. Now, so basically it is very uncommon that the blades will be symmetrical, right. So, what we can assume that this is the geometrical similarity of the this rotor disc, but if blades are not symmetrical, then beta 1 is not equal to beta 2. So, beta 1 is not equal to beta 2, we assume that blades are not symmetrical. You know that we had discussed for the impulse turbines that beta 1 equal to beta 2, right, because it is a true case for the impulse turbine, because most of the impulse turbines are having symmetrical blades. So, basically beta 1 equal to beta 2 is a case, a true case for the impulse turbine, but this is not a case for the reaction turbine. Okay. So, if this is beta 1 is not equal to beta 2, then if we go back to the velocity triangles, if we try to recall that for impulse turbine, you know, I am now marking here that say this is a particular point, say this is F. So, let me write here that for steam turbine, the ratio of absolute velocities, that is W2 by W1, when steam is passing through the moving blades or blades, the ratio of absolute velocities W2 by W1 is known as blade friction factor Kb, right. So, because of the losses due to friction, this W2 is always less than W1. So, that means the relative velocity of steam, which is when it is entering into the first row of blades or moving blades, is W1, but the relative velocity of steam coming out from the first row of blades or moving blades is W2, and W2 is less than W1, and it is because of the frictional losses. So, this Kb is always less than 1, and now you can understand it is because of this W2 less than W1. If you try to recall the velocity triangles for the impulse turbine, we had seen that there is basically drop of axial or drop in axial velocity, but we can understand that the relative velocity is now extended up to point D. So, basically this much increase in relative velocity of steam when it is coming out from the first row of blades or moving blades is due to the increase in velocity of steam when it is passing through the blades in case of a reaction turbine, and that is solely due to drop in pressure. So, try to understand, let me tell you this once again. So, for the impulse turbine, W2 is always less than W1, and we can see for this case, for this particular case is that W2 is extended up to point D. So, this increase in relative velocity of steam when it is passing through the first row of blades or moving blades is due to the increase in steam velocity, and that is solely due to drop or pressure drop, and that is what we had discussed here. So, basically it is because of this pressure drop, the velocity of steam, that I said that the kinetic energy, there will be an increase in kinetic energy of the steam, which in turn is also responsible for the increase in relative velocity that we can see from here. So, this is increase in relative velocity. Due to pressure drop. Okay, due to pressure drop. So, if we now see this diagram, we can see that the that is no axial thrust. So, there is no axial thrust because delta C A equal to 0. That means that for 50% reaction turbine, for which for 50% reaction turbine for which C2 equal to W1, and this is the blade angle at the inlet, there is no axial thrust, but we can't say like this, there will be a small amount of axial thrust that is solely due to change in pressure when steam is passing through the first row or second row or third row of blades or moving blades. So, basically a change in pressure of steam when it is when it passes through the blades or first row of blades or second row of blades, a small amount of axial thrust would be there, and but there is no axial thrust that we can see particularly for this type of turbine, that is 50% reaction turbine from this diagram. Okay. So, there is no change in axial velocity. So, basically C A 1 equal to C A 2, that we can see from this diagram. Hence, delta C A, that is C A 1 minus C A 2, these two are, I mean the difference of this between these two velocity components is 0. So, that is there is no axial thrust, but as I said, a small amount of axial thrust would be there, and it is because of this change in pressure or pressure drop when steam is passing through the blades. So, now our next objective should be to calculate delta C theta, that is the change in swirl component of velocity or wall component of velocity, and which is responsible for the tangential thrust. So, basically there is no axial thrust that we have discussed. So, let me write here. So, delta C A equal to 0, no axial thrust for 50% reaction turbine. But as I said, small amount of axial thrust would be there, due to change in pressure of the steam as it passes through the blades. Now, if we try to quantify delta C theta, that is C theta 1 minus C theta 2. So, this is C A 1 minus C A 2. So, this is equal to 0, that is C A 1 equal to C 2. That means, I will come to this particular point later today. So, C theta 1 minus C theta 2. Now, see, if we measure the angles in the clockwise direction, then delta is greater than 90 degree, that we can see. So, when delta greater than 90 degree, then to get this change in swirl velocity delta C theta, these two components are added together. So, basically it should be plus when delta is greater than 90 degree, and it should be minus when delta less than 90 degree. Let me tell you once again, we have measured the angle in the clockwise direction. Now, delta is greater than 90 degree. For this case, if you would like to quantify or if you would like to estimate the swirl component of velocity, the change in swirl component of velocity delta C theta, then we have to add C theta 1 C theta 2 together. That means, we have to add the swirl component of velocity together to obtain the change in swirl component of velocity or to estimate this change in swirl component of velocities. But when delta less than 90 degree, then one component or C theta 2 should be subtracted from C theta 1. So, now for this particular case, delta C theta equal to C theta 1 minus C theta 2. So, we can predict what would be C theta 1. So, C theta 1, say this is C theta 1. So, this is C theta 1 and this is C theta 2, right. So, C theta 1 is C 1 cos alpha. So, this is C 1 cos alpha minus C theta 2, C theta 2 is C 2 cos 180 minus delta, right. So, we can write C 2 cos 180 minus delta, that is equal to C1 cos alpha, C1 cos alpha, C1 cos alpha minus, so plus C2 cos delta, plus C2 cos delta. Now, this C2 cos delta, C2 cos delta, again we can write that is equal to W2 cos beta 2 minus Vb. So, this small component d, small component C equal to, this is B E minus B C. So, we can write C E equal to B E minus B C. So, C E equal to B E minus B C, that we can see from this particular figure, B E minus B C and B equal to W2 cos beta 2 minus V B. So, this is W2 cos beta 2 minus V B, right. So, we can write again delta C theta equal to C1 cos alpha plus W2 cos beta 2 minus V B. Now, if we go back to the previous slide, we can see this is W1. So, this is W1 because this is W2, rather this is W2 cos beta 2. So, this is not W1, this is W2. So, this is W2 cos beta 2, right. Now, see, we have discussed in the beginning that W2 equal to C1 for R equal to half, that you will be getting if you equate the enthalpy drop across the moving blade and enthalpy drop across the fixed blades, and beta 1 equal to alpha because of the geometric similarity. So, that means W2 equal to C1 and beta 1 equal to alpha, right. So, we can write, so and so basically what we can write that beta 2 equal to alpha 1, this beta 2 equal to alpha. So, this is beta 2, this is beta 2, this is beta 2 because the geometric similarity, not alpha 1. So, angle DBC equal to angle ACB. So, angle DBC, that is beta 2, not beta 1. By mistake I wrote it beta 1, but it should be angle DBC. So, beta 2. Now, what we can see that W2 equal to C1 and beta 2 equal to alpha. So, we can write this expression in this form, that C1 cos alpha plus C1 cos alpha minus V B, because beta 2 equal to alpha and W2 equal to C1. So, that means we are getting this is equal to 2 C1 cos alpha minus V B. So, basically we are trying to calculate the change in small component of velocity which would be responsible for the tangential thrust, right. It is also possible that you can calculate this, because you know that this C theta 2 equal to W1 cos beta 2 plus W2 cos beta 2. So, that means I am writing that delta C theta 2, delta C theta equal to W1 cos beta 1 plus W2 cos beta 2, right. W1 cos beta 1, if we go back to the previous slide, W1 cos beta 1 equal to C1 cos alpha minus V B. So, this is C1 cos alpha minus V B plus W2 equal to C1 and beta 2 equal to alpha. So, cos alpha. So, this is basically 2 C1 cos alpha minus V B. So, we can understand that this change in solved component of velocities, that is delta C theta equal to 2 C1 cos alpha minus V B. So, we can calculate delta c theta which would be responsible for the tangential thrust. Now, we can calculate, you know that what would be the tangential thrust. So, if we calculate the tangential thrust, or if we write tangential thrust equal to this delta c theta into tangential thrust would be equal to delta c theta into mass flow rate of steam, right. So, from there we also can calculate what would be work transfer or diagram work. So, basically the work transfer, if we also can write the work transfer that is equal to delta c theta into V b, right. So, or blade or diagram work. So, this is work transfer or diagram work. Now, we are getting this work transfer diagram work, this is per unit mass of the steam flow rate. So, if we try to quantify what would be, so basically tangential thrust into V b is the work transfer or diagram work, tangential thrust is delta c theta into mass flow rate of steam. Now, we are trying to quantify work transfer or diagram work per unit mass of steam flow, then it is delta c theta V b by m s. So, basically work transfer or diagram work per unit basically mass flow of steam. So, this is steam. Then this is the amount of work that we can extract at the cost of some input energy. So, if we now try to quantify the blading work or diagram or blading efficiency or diagram efficiency, then we also need to write the input energy. We need to know the input energy per unit mass flow of steam. So, input energy per unit mass flow of steam equal to, it would be equal to say C 1 square by 2 plus, that is very important, that W 2 square minus W 1 square by 2. So, W 2 square minus W 1 square by 2, because this is the input energy per unit mass of steam, right. We had seen that for the reaction turbine there is an increase in kinetic energy of steam because of the decrease in pressure, and that effect also should be taken into account, that what is the input energy given to get this amount of work output. So, what is we know that, so if we write that input energy equal to C 1 square by 2 plus W 2 square minus W 1 square by 2. So, we know that is C 1 square by 2 plus C 1 square by 2 minus W 1 square by 2, because we know W 2 equal to C 1, and that is from the previous discussion, because for this is valid for the 50% reaction turbine. So, this is C 1 square minus W 1 square by 2, right. Now, we need to write W 1 in terms of the known quantities, that is the velocity of steam which will come out from the nozzle, that we know. Also, we know the blade velocity V b. So, if we look at the velocity triangle, that is A B C, that velocity triangle, if we know, if we look at, we can write this cos alpha, that is alpha is also known. So, cos alpha equal to C1 square minus C1 square plus Vv square minus W1 square by 2 C1 Vv. So, from there we can write W1 in terms of known quantities, that is C1, Vv and alpha. So, here we can write from triangle ABC, from triangle ABC we can write cos alpha equal to C1 square plus Vv square minus W1 square divided by 2 Vv into C1. That means W1 square equal to C1 square plus Vv square minus 2 Vv C1 cos alpha. So, if we write this expression here, this is the input energy, then we can write the efficiency, diagram efficiency. So, let me tell you once again, tangential thrust would be that delta C theta into mass flow rate of steam. Since we are trying to estimate the work transfer or diagram work per unit mass flow of steam, so the tangential thrust multiplied with Vv is the work diagram work. Now, per unit mass flow of steam, that ms will get cancelled, and then we are writing delta C theta Vv, and this is the work that we are getting at the cost of this input energy, and we could write the final expression of input energy is like this, that is C1 square minus W1 square by 2. So, input energy equal to, that would be equal to C1 square minus Vv square, right, plus 2 C1 Vv cos alpha divided by 2, plus 2 C1 Vv cos alpha divided by 2. Because this C1 square by 2, C1 square minus C1 square by 2 would be C1 square by 2. So, that is why it is C1 square by 2. Now, this is the input energy, and at the cost of this input energy we are getting work output diagram work output or blading work output, that is equal to, so this is input energy per unit mass flow of steam. So, work output, this is also per unit mass flow of steam, because while we are trying to estimate the efficiency, the unit will remain same. Now, if we write it, then what we are getting is, that this diagram efficiency eta d, then diagram efficiency or blading efficiency eta d, that would be equal to delta C theta into Vv, right, that is 2 C1 cos alpha minus Vv into Vv. So, this is 2 C1 cos alpha minus Vv into Vv divided by this quantity. So, we can write C1 square minus Vv square. So, basically 2 will go here, and C1 square minus Vv square plus 2 C1 Vv cos alpha, right. So, we can write one step further, that we can write like this 2 Vv square into, so basically we are taking Vv out from this from the quantity written in bracket. So, it would be 2 C1 by Vb cos alpha minus 1, and if we take C1 square out from this, then 1 minus Vb square by C1 square plus twice Vb by C1 cos alpha, right. So, this is the expression of blading work or diagram work. See, we can see that Vb by C1, that particular ratio is there. So, that means we also try to cast this expression of blading efficiency or diagram efficiency in terms of the velocity ratio, that is Vb by C1. So, that means we can write eta d equal to 2 Vb by C1 third square, 2 Vb by C1 whole square. We can write eta d equal to 2 Vb by C1 whole square, and then we can write 2 cos alpha divided by Vb by C1 minus 1. So, that is what we can write. Right? We can write, and then we can write 1 minus Vb by C1 square plus 2 Vb by C1 into cos alpha. So, that is 1 minus Vb by C1 whole square plus 2 Vb by C1 cos alpha plus 2 Vb by C1 cos alpha. So, that means we can see that the efficiency, the diagram efficiency or blading efficiency is function of one ratio, that is the velocity ratio. Right. So, this is the velocity ratio. We had discussed about this particular ratio in the context of impulse turbine. So, again we can see that the diagram efficiency or blading efficiency of the reaction turbine can also be expressed in terms of velocity ratio. Now, you try to understand, there is a particular value of this ratio for which the diagram efficiency will be maximum, and to obtain that optimum velocity ratio, what we need to do? We need to differentiate eta d with respect to this quantity and equating it to 0. So, that means particular value of Vb by C1 for which the diagram efficiency or blading efficiency will be maximum, and that means what we need to do? We need to differentiate eta d with respect to Vb by C1 and then equating it to 0. We will be getting Vb by C1 optimum. Particular value of Vb by C1 for which the diagram efficiency will be maximum is the optimum velocity ratio, that is Vb by C1 optimum, and this Vb by C1 optimum for this particular case is C1 cos alpha, C1 cos alpha. So, but I am not going to do this task here. So, if you differentiate eta d with respect to Vb by C1 and then if we equate it to 0, then we will be getting Vb by C1 optimum is equal to C1 cos alpha 1, and then eta d maximum would be equal to, so maximum diagram efficiency will be equal to 2 cos square alpha by 1 plus cos square alpha. So, that is, so let me write here in the next slide. So, that means we can write the optimum speed ratio V b by C 1 optimum equal to C 1 cos alpha and maximum diagram or blading efficiency eta d maximum equal to 2 cos square alpha 2 cos square alpha divided by 1 plus cos alpha 2 cos square alpha divided by 1 plus cos square alpha. So, that means we have an maximum diagram work. You can understand the diagram work is delta c theta into V b and delta c theta equal to 2 cos alpha minus V b. So, that means it would be 2 cos alpha minus V b into V b. So, that is 2 cos alpha minus V b into V b, and so you can understand this 2 cos alpha minus V b, because we have obtained that V b by C 1 equal to C 1 cos alpha 1. So, that means C cos alpha 1 is equal to V b, right. So, this is 2 C 1 cos alpha minus V b into V b, and 2 C 1 cos alpha equal to V b minus V b into V b, because V b by C 1 optimum equal to cos alpha. So, that means V b square. Now, very quickly I will tell what would be the velocity triangles, particularly for this case when diagram efficiency would be the maximum efficiency, diagram work would be the maximum work for a 50% reaction turbine. So, if we try to understand that diagram work, that is given delta c theta into V b equal to V b square, right. So, what is so basically try to understand. So, diagram work equal to V b square. So, that means delta c theta into V b equal to V b square. Therefore, delta c theta equal to V b. Therefore, 2 cos alpha minus V b equal to V b. Therefore, V b equal to cos alpha. So, V b equal to cos alpha, this is 2 C 1 cos alpha. So, V b equal to cos alpha C 1 cos alpha. So, V b equal to C 1 cos alpha, that means that is basically V b by C 1 equal to cos alpha. So, that is the optimum speed ratio. Now, you can understand C 1 cos alpha equal to V b. So, this is W 1, this is C 1, this is W 2 and this is C 2. So, this is V b. So, C 1 cos alpha equal to V 1, C 1 cos alpha equal to V b, that we can see from this diagram. The velocity triangles for 50%. So, this is beta 2, and this is beta 1. So, this is the velocity triangles for 50% reaction turbine producing maximum diagram work. So, let me tell you once again, this is the velocity triangle, I mean these are the velocity triangles of the reaction turbine having degree of reaction equal to half when producing maximum work. Okay. So, to summarize, today we have discussed about the reaction turbine. From the velocity triangles, we have tried to estimate the diagram work, tangential thrust and finally diagram efficiency. We have quantified the optimum ratio for which the diagram efficiency is maximum. From there, we have also tried to we have also tried to predict the velocity triangles for a 50% reaction turbine producing maximum work. So, with this I stop here today and we shall continue our discussion in the next class. Thank you.